All right, well, let's continue with our problem. All right. So our goal is to find the energy states for the particle in a finite well. All right. And what we've done is to set up the problem, and we've reduced the problem to a simpler form for the case where we find even parity solutions. Okay. We expect, for example, that the ground state will be an even parity solution. Okay. Here, let's go to the notebook and continue. Okay, so remember our problem. We're trying to find the energy states for this system here, the finite well. Okay? And we can look now for we're looking now for the even parity solutions. Hey, just to remind you, if we had set up our square well, our infinite well, in the same way, then you can see that the n equals 1 state, and n equals 3 state, and n equals 5, and so on. Those would be even parity states. Whereas the next state, like n equals 2 and n equals 4, and so on, those would be odd parity states. All right? And we expect to find the same pattern for the finite well. Okay, just wanted to mention that. Very good. So we've set up our problem here. And so now let's see what this means, okay? So the first boundary condition tells us that the wave functions have to be equal at L/2. That means that wave function 2, or C, times cosine k times L/2, since that's what x is at the boundary, that's equal to wave function 3 at L/2. That is d e to the minus alpha times L/2. Okay? The second condition tells me that the first derivatives are equal. So now we have to consider the first derivative of this function with respect to x. That would be the derivative of cosine is is minus sine, okay? So we would have minus k times c times sine k L/2. And this has to be equal to the first spatial derivative of this function, which would be minus alpha d times e to the minus alpha L/2. All right? Those are the two equations that we have to solve simultaneously. Okay? All right. Now we're going to simplify this with a trick, okay? The trick is this. What we're really interested in now is finding an equation for K or for alpha, since either of those would tell us what the energy is, all right? We're not so interested in looking at exactly what the wave function looks like, so we don't really care about C and D right now. So let's combine these to get an equation that doesn't have C or D in it. Here's the trick. Let's look at the ratio of equation 2 divided by equation 1, all right? Well, that tells me that in that case, we have minus kc sine kL/2 equals d e to the minus alpha L/2. But now we're dividing on both sides by the other equation. C times cosine kL/2 is equal to, oh, I'm sorry, I left out a minus alpha here. And we have d e to the minus alpha L/2 here. You see what we've done? Well, what's neat about this is that when we do that, many things cancel out. C and D cancel out. The negative sign cancels out, okay? And the exponential term, e to the minus alpha L over 2, cancels out as well. And here's what we're left with. We're left with K times sine KL over 2 divided by cosine KL over 2. That's equal to alpha. All right? Or even more simply, K times tangent KL over 2 is equal to alpha. Okay, so by using that trick, we found a property of the solution that every even energy state must have, which is that K times K alpha over, KL over 2 must equal to alpha. All right? Perfect. Okay. Now, you might be saying, great, but what do I do with this equation? The first thing I want you to do is to recognize that this is an equation for energy. Here, let me rewrite this slightly. I'm just going to divide on both sides by K. There we are. Okay? And then let's see. Remember, K here is equal to square root of 2me over h bar. And alpha is equal to something rather similar. Oops. Square root of 2m u naught minus e over h bar. Notice that both of these functions have only one unknown in them, e. So once we specify e, we've specified both alpha and k. The only problem is if we write this equation here as an equation for e, which I'll do, it's going to look very complicated. When I find alpha over k, some common terms will cancel out, and we'll get so we'll get an equation for the energy. Here it is. And well, I suppose that's all we need to find the energy states. We just have to look for solutions of this formula. But the only problem with this is that this particular equation is what's called a transcendental equation. It's an equation that can't be solved analytically, all right? Although you're welcome to try. So it seems like we're at an impasse, but not really. Remember, just because an equation can't be solved analytically doesn't mean it can't be solved. It can always be solved numerically. And I'll show you how we can solve this equation numerically in the next video.